Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to look at the periods in AI history, often called the AI winters, and explore what caused them and what lessons they left behind.
And you really can't understand the energy and, frankly, the nervousness around today's AI boom without grasping this history.
Right.
The whole story of artificial intelligence is it's completely cyclical. It's this dramatic pattern of spectacular, often way overhyped summers, followed by these abrupt, really painful freezes.
The busts.
Exactly, the busts. These are true boom and bust cycles, and they're driven not just by the technology, but by finance, and maybe most importantly, by human expectation.
So when we talk about an AI winter, we're not talking about a technical decline where the research just stops.
No, not at all.
We are talking about a commercial and financial collapse, a sharp, sometimes catastrophic drop in funding, and just as important, a huge drop in public interest and confidence.
Right. The field really does divide so neatly into these warm seasons, the summers, where money is just flowing freely, and then the cold seasons, the winters, where everything just tightens up.
And that metaphor, the winter, it has a very specific origin that I think really speaks to that core issue you mentioned, expectation management.
It does. And it wasn't even coined during the first actual freeze back in the 70s. It came much later, in 1984.
That's right. You had leading researchers like Roger Schenck and the legendary Marvin Minsky, who had already lived through the big disappointments of the 1970s.
Right. They'd seen this movie before.
Exactly. And they saw the new enthusiasm for expert systems in the mid-'80s just spinning wildly out of control. They recognized that pattern of, irrational exuberance.
So they held this famous public debate. It was at the Association for the Advancement of Artificial Intelligence, the CHAI meeting that year. And they stood up and basically warned the business community that the promises being made were completely unsustainable.
And they were worried that the inevitable disappointment, when reality just failed to meet the hype, would cause funding cuts so severe they would be. What was the phrase they used?
They compared it to a nuclear winter. They meant a total stop to all serious long-term research.
Wow. That's a powerful analogy.
And sadly, a very prescient one for what would happen just a few years later.
So for our conversation, we're really focusing on two major historical cycles. That first winter, which hit hard around 1974 and lasted into 1980, and then the second one.
Which was a much longer and I think a more profound freeze. It started around 1987 and didn't really start to thaw out until around the turn of the millennium.
And what becomes so clear when you look at these periods is that the winters, as devastating as they were for careers and companies, they were actually necessary corrections.
Absolutely necessary. They forced the field to abandon its often fantastical goals and adopt much more rigorous, practical, and mathematically grounded approaches. They were really the price that was paid for making all those unrealistic promises.
Okay, so let's start with the period that came before that first big crash, the first summer of AI. This is right after the 1956 Dartmouth conference.
Which is pretty much the official birthplace of the field, yeah.
And the mood was just electric. You had researchers like Herbert Simon already predicting that within a decade, a computer would be the world chess champion.
And discover a major new mathematical theorem. The optimism was boundless.
So where did that confidence come from?
It came from some real, pretty narrow early successes, specifically in what we now call symbolic manipulation.
And the core idea there was that human thinking logic, reasoning, all of it, could be captured just by manipulating symbols according to a set of rules.
Exactly. And Newell and Simon's logic theorist, or LT, is the perfect example. This was a program dedicated to proving theorems in symbolic logic, which is, an incredibly complex task for a human.
And how did it do?
It was astounding. For the time, LT didn't just work. It managed to prove 38 of the 52 theorems in a chapter of this famous canonical text, Principia Mathematica.
That's impressive.
It gets better. In one famous instance, the program actually found a proof for a theorem that was shorter and more elegant than the one the authors themselves had published.
No way.
Yes. So you can imagine what they were thinking. They thought they'd crack the code of general intelligence, just give the machine a starting point and the rules, and it would just reason its way to the answer.
But that hubris grew fast, and the first major disappointment didn't come from logic, but from a much more pragmatic, high-stakes application, machine translation.
And this was all about the Cold War, right? That was a big driver. The U.S. government, we're talking the CIA, the National Research Council, they poured a ton of money into this starting in the mid-50s. They were desperate for automatic translation of Russian scientific documents and military reports.
And of course, the media hype was instantaneous.
Oh, yeah. You hear about the 1954 Georgetown IBM demonstration, and the headlines were just explosive. Things like, robot brain translates Russian into King's English.
That was a setup, right?
A textbook case of an inflated demo. They had basically hand-fed the machine this tiny, curated dictionary of about 250 words and 49 very specific Russian sentences. It was completely canned.
But the public saw that and imagined they were just months away from seamless, instant translation of anything.
Of course. But in reality, researchers immediately slammed into this deep, messy problem of semantics, of meaning, specifically, word sense disambiguation.
How do you tell a machine which bank you mean? A river bank or a money bank?
Exactly. How do you program a rule for that when the meaning is entirely dependent on context and real-world knowledge? The symbolic systems of the time just couldn't handle that ambiguity.
There's that famous example, right, with the phrase, the spirit is willing, but the flesh is weak.
Right. They supposedly translated it into Russian and then back into English, and the machine spat out something like, the vodka is good, but the meat is rotten.
Which perfectly illustrates the problem. Without any common sense, these rule-based systems just break down in these bizarre, almost comical ways.
And this failure, after a decade of massive investment, led the National Research Council to finally act.
So by 1964, they were getting pretty worried.
Deeply concerned about the lack of progress, so they formed the Automatic Language Processing Advisory Committee, or ALPAC. And when the ALPAC report was published in 1966, it was devastating.
What did it say?
It concluded that machine translation was, and I'm quoting here, slower, less accurate, and more expensive than human translation.
So not only was it not working, it was actually worse than the old way of doing things.
Exactly. So after spending about $20 million, which was a huge sum for research back then, the NRC just ended all support. The whole field of natural language processing essentially froze, and a lot of careers just ended overnight.
That's a huge blow in the U.S. But the event that really kicked off the full winter, especially in the UK, was the Lighthill Report in 1973.
Yes. Sir James Lighthill. He was a leading applied mathematician, and the British government commissioned him to evaluate the state of AI research over there. His report is, it's one of the most destructive academic assessments in history.
And his main criticism was what?
That AI research had shown an utter failure to meet its grandiose objectives, and that anything AI was doing could be done in other, more rigorous scientific fields.
So he was basically saying it was all smoke and mirrors.
It was. He divided AI work into 3 categories. Category A was trivial stuff. Category B was basically just control theory with a fancy AI label. And Category C, the big central challenge of complexity and scale, he believed that would never be solved. It was a complete academic takedown.
And the results?
Immediate and catastrophic. The UK government completely dismantled most of its AI research funding. Progress just halted for over a decade. So you take the ALPAC failure, the Lighthill Report, and this growing disillusionment in the U.S., and that's what officially ushered in the AI winter of the 1970s.
But it wasn't just these external reports. The researchers themselves were hitting some massive, fundamental technical wall.
Oh, absolutely. It was happening from the inside, too. They had believed in what we call the scaling up assumption.
Meaning that if they could solve a small, simple problem, a toy problem, they just needed faster hardware and more memory to solve a complex real-world one.
Precisely. They worked in these controlled environments, like Minsky's microworlds. The famous one is the blocks universe, where a robot arm has to manipulate simple colored blocks. In that world, simple logical steps combine very neatly for success.
But the real world isn't a bunch of colored blocks.
Not even close. As soon as they tried to introduce the complexity of the real world with all its variables and nuance and ambiguous data, they just slammed right into the reality of the combinatorial explosion.
That's the technical iceberg right there.
It is. The field of computational complexity theory was really developing at this time, and AI researchers were learning, the hard way, that the number of possible solutions for real problems doesn't grow in a straight line. It grows exponentially.
Can you give us an example?
Sure. Take a simple planning problem. If a solution requires, say, 10 steps, and each step has only 3 possible options. The total number of paths you have to search is, well, it's astronomical.
So even if your hardware was doubling in speed every year.
The problem size was exploding at a pace the hardware could never, ever keep up with. You couldn't search the whole solution space, and their little shortcuts, their heuristics, they just weren't smart enough to reliably cut down that search.
So the general problem solvers ended up solving
Almost no real-world problems. They became computationally intractable almost immediately.
And this problem wasn't just for the symbolic, rule-based systems. The other big approach at the time, the connectionist school, what we now call artificial neural networks, they suffered their own major setback right before the freeze.
This is the famous perceptron story. Frank Rosenblatt built the markup perceptron back in 1957. It was a single-layer network, a physical machine that could actually learn through trial and error. A huge success, and really a forerunner of deep learning.
But that excitement didn't last long.
No. It was basically squashed in 1969.
And that's when Marvin Minsky and Seymour Papert published their book, Perceptrons.
Yes, and that book was incredibly influential. Minsky and Papert laid out this rigorous mathematical proof of the fundamental limitations of a single-layer perceptron. The most famous proof showed that a single-layer network could not solve problems that weren't linearly separable.
Like the XOR logical function.
Exactly. XOR, the exclusive OR, is super simple for a human. But for a single-layer network, it's impossible because you can't draw a single straight line to separate the correct outputs.
But they knew about multi-layer networks even then, right?
They did. The potential of multi-layer perceptrons to overcome this was known in theory. But, and this is the key part, Minsky and Papert emphasized that no one at the time had any practical way to train those multi-layer networks.
So their conclusion was taken by funding bodies as
a general condemnation of the entire neural network approach. It was a really powerful, and some would say politically charged, criticism from these two giants of the symbolic school against their rival connectionist school. It basically put neural network research into a deep freeze for decades, right as the winter was starting.
Meanwhile, the U.S. government's main funder, DARPA, was starting to demand results.
Yeah, the old model of just funding people, not projects, was over. The Mansfield Amendment in 1969 changed all that. Now, all government funding had to be tied to clear, mission-oriented goals.
They wanted deliverables. And the big disappointment for them came from their speech understanding research program, the SUR program.
They'd invested millions hoping for a system that could, say, take voice commands from a fighter pilot in a cockpit.
And what did they get?
By 1974, after years of work, the systems they produced, like one called Harpy from Carnegie Mellon, could recognize spoken English. But only if the vocabulary was tiny and the words were spoken in a very specific, predetermined order.
So if you went off script at all?
The whole system just broke. It showed that the only reason it worked at all was because they had hardwired all this knowledge into it, which completely limited its general use.
The DARPA folks must have felt like they'd been had.
They felt completely misled. In 1974, they canceled a huge multi-million-dollar contract. There's a great quote from the time saying some funders basically wanted to teach these people a lesson by cutting their funding to force some humility and practicality on them.
It's just that recurring theme, isn't it? The failure was rooted in this fundamental philosophical mistake.
It was. Early AI focused too much on trying to replicate human thinking, and they just utterly underestimated the complexity of the real world and the sheer difficulty of scaling up their systems. That focus on general purpose intelligence just failed completely.
And that failure led directly to a massive and I guess necessary strategic shift that defined the next era.
It did. Researchers were forced to get pragmatic. They stopped chasing that general purpose holy grail, and they focused on something much, much narrower. Knowledge-intensive expert systems.
So this was the big lesson from the first winter. Don't try to build a general mind, build a highly specialized tool. And this kicks off the second summer of AI.
Exactly right. The strategy shifted to mastering these extremely narrow domains of human expertise. The systems had to embody deep, specialized human knowledge, usually captured as thousands of if-then rules, not just basic logic.
And one of the earliest successes was a system called Dendrol, right? Developed at Stanford.
Yeah, Dendrol was a true pioneer. It was designed to figure out the molecular structure of unknown organic compounds from mass spectrometry data. It was seen as the first really effective knowledge-intensive system because its power didn't come from just searching blindly. It came from incorporating the specific rules of chemistry, true expertise.
And then from that same research group came ICIN in the mid-'70s. This one is probably the most famous early expert system.
It is. MYCIN was designed to diagnose severe blood infections and recommend the right antibiotic dosages.
Yeah, and it worked.
It was revolutionary. It showed near-human performance. In fact, it was often better at diagnosing these infections than medical interns were. It was built around something like 600 rules that they got from painstaking interviews with medical specialists. And, crucially, it could handle uncertainty. It assigned confidence factors to its diagnoses, which was a huge leap from the brittle black-and-white logic of the 60s.
But the thing that really lit the fuse on the commercial boom came in the early 80s with a system called R1, later named XCON.
Ah, yes, XCON for Digital Equipment Corporation, or DEC.
Its job was purely business. It configured these complex VAX computer systems for customers. It basically acted as the human expert who knew all the compatibility rules for thousands of different components.
And the financial impact was just staggering. This wasn't some academic paper, this was commercial proof. Within just a few years, XCON was estimated to have saved DDC tens of millions of dollars a year.
Wow.
Just by reducing errors in orders that used to require these human configuration experts, that kind of documented massive financial success, it opened the floodgates.
And the whole AI industry, which had been basically dead, just exploded.
It grew into a multi-billion-dollar market by the late 80s. You had all these specialized companies popping up, selling expert systems, vision systems, robotics components. It was a frenzy.
And this boom immediately sparked this fierce global competition.
It did. In 1981, Japan announced its super ambitious fifth-generation project. They committed over $850 million to develop intelligent systems machines that could converse, translate, and reason just like people.
And the U.S. government and industry just panicked, fearing they were falling behind.
They responded with incredible urgency. They launched these big consortia like the Microelectronics and Computer Technology Corporation, MCC, in '82, specifically to keep pace. The excitement was just palpable. Everyone believed AI was finally delivering.
And yet, just like Minsky and Schenck had warned back in '84, the whole thing came crashing down again. This was the second deep freeze, and this time it was hardware that triggered the collapse.
It was an abrupt, spectacular failure that started around 1987. And the problem was the software infrastructure of the time.
Most of the complex AI software in the U.S. was written in LASP, right?
Right. LASP was the perfect programming language for symbolic manipulation. It handles memory really well. But running LASP required these highly specialized, incredibly expensive pieces of hardware called LASP machines.
Why did it need its own dedicated machine?
Because LASP is so memory-intensive, it relies on complex data structures, not simple math. So LASP machines were built with a special hardware architecture that made processes like garbage collection managing memory extremely fast. And companies like Symbolics were selling these things for astronomical prices. It was a huge $500 million industry all on its own.
And that dependence on specialized hardware proved to be a fatal flaw.
It did, because by the mid-'80s, the revolution in general-purpose computing was accelerating. Moore's Law. You had workstations from companies like Sun Microsystems, and pretty soon just regular desktop PCs that were becoming incredibly powerful.
And they could run LASP just fine.
They could run high-performance LASP environments efficiently and, more importantly, cheaply. So suddenly, your specialized LASP machine that cost hundreds of thousands of dollars was obsolete. A standard workstation costing a fraction of that could do the job, and often do it better.
So the entire business model just evaporated.
Almost overnight. It was an immediate, brutal market correction. This specialized hardware that was propping up the whole software boom just vanished, and that triggered the financial winter.
But even if the hardware hadn't collapsed, the expert systems themselves were proving to be commercially unsustainable. They had these really core limitations in practice.
Yeah, their commercial life was just plagued by what we call the knowledge acquisition bottleneck and the problem of brittleness.
Okay, let's break down that first one, the knowledge acquisition bottleneck.
Well, these expert systems like MYCIN or XCON, they needed this huge database of rules that they got from human experts. Acquiring that knowledge was this painstaking, super time-consuming process. And worse, the knowledge in any field medicine, computers, whatever, is constantly changing.
So updating the knowledge base was a nightmare.
An incredibly expensive nightmare. The maintenance costs were just astronomical. Most companies ultimately couldn't afford it.
And then there was the brittleness. They were amazing in their narrow little domain, but completely useless outside of it.
Because they had zero common sense. If you gave them an input that was even slightly outside their pre-programmed scope, they would make these bizarre, nonsensical, sometimes even dangerous errors, the same kind of weird behavior we saw with the early machine translation. And they were totally opaque. They couldn't tell you why they made a weird decision, which makes them unusable in any field where you need accountability.
At the same time, the big government programs that had fueled all the hype were also failing.
Japan's big fifth-generation project, despite all that money, it completely failed to meet its goals. It ended not with a successful roar, but with a whimper by 1992.
And the same thing happened in the U.S. with the Strategic Computing Initiative.
Yeah, when new leadership took over at DARPA in '87, they were deeply skeptical. The new director saw expert systems as nothing more than clever programming and just directed funding away from AI research. It was a profound, painful cut.
So the lesson was the same, but maybe even more severe this time.
Much more severe. The industry had been too reliant on hype, on specialized hardware, and on this knowledge engineering process that just didn't scale commercially. This second winter lasted for well over a decade, and it fundamentally changed the identity of AI research.
Which brings us to that really harsh period, the late 80s and all through the 90s. The stigma around the term artificial intelligence became so toxic that researchers just actively avoided it.
Absolutely. No one wanted to be called an AI researcher anymore. You'd be seen as a wild-eyed dreamer chasing impossible goals. So they rebranded completely. They started calling their work machine learning, analytics, informatics, intelligent systems, anything but AI, just to get funding.
And this conservative shift was necessary for survival. It meant moving away from that rigid, brittle, rule-based reasoning.
And moving towards statistical and mathematically rigorous approaches. And this is probably the most important lesson to come out of the winters. The field embraced rigor. You see the rise of models that dealt explicitly and mathematically with uncertainty. Hidden Markov models, or HMMs, became central.
HMMs are key for things like speech and handwriting recognition. And their mathematical basis, using probability to model sequences, it just provided a level of academic rigor and reliability that was totally missing before.
Exactly. HMMs, and crucially, the adoption of probabilistic reasoning, like Bayesian networks from Judea Pearl, allowed researchers to model decision-making where the outcome was uncertain. This was a radical shift from the all-or-nothing logic of symbolic AI, and it gave industry a new level of confidence because the results were scientifically measurable.
And even the connectionist school, the neural networks that Minsky had basically put on ice in '69, started its quiet comeback during this winter.
It did. The key theoretical advance was the revisiting and popularization of the backpropagation algorithm around 1986. This algorithm is the fundamental learning mechanism for training multi-layer neural networks. The theory had existed before, but its practical application was rediscovered and refined by multiple groups, and that created the groundwork for the massive success of deep learning years later.
The field also learned the vital lesson of accountability and measurement. The 90s saw the development of these shared, standardized datasets.
This was a critical step in rebuilding trust. You had projects creating things like the MNIST dataset of handwritten digits, the Yale Face database, and others, and having these public benchmarks meant that researchers couldn't just claim great performance on their own little toy problems anymore. They had to show rigorous, reproducible progress on shared objective challenges.
So this quiet, conservative shift allowed AI to survive. But the public didn't really notice again until the late 1990s when AI got this massive global symbolic victory.
Deep Blue, IBM's chess-playing AI defeating the world champion Garry Kasparov in 1997.
It was a huge cultural event, right? Televised, followed everywhere. It signaled that machines, now built on these rigorous, highly optimized methods, could finally surpass human capability in these complex but still defined domains.
And that victory happened right as three huge technological factors were converging, creating the perfect storm to ignite the third summer of AI.
And those were?
An abundance of data, unprecedented computing power, and fundamentally better algorithms.
Right. We had Moore's Law just exploding and the rise of the global internet in the late 90s and early 2000s. The big data revolution.
And data was the fuel. Suddenly we were generating these massive, unprecedented volumes of data text, billions of images, voice recordings, medical records. Data, the one thing that was critically missing in the 70s and 80s, was now everywhere.
But you had to structure it.
Right. Which is why in 2009, ImageNet was created. A colossal database with millions of images, all neatly labeled by humans. This provided the massive amount of fuel needed to train complex visual recognition models.
And then came the hardware breakthrough. To train networks on millions of images, you needed specialized power. And that was the graphics processing unit, the GPU.
Which was traditionally used for video games.
So why did the GPU become the key hardware for AI?
Because of parallelism. Training deep neural networks means doing billions of matrix multiplications, just multiplying large grids of numbers together. And GPUs are designed to do thousands of these calculations all at once, in parallel. CPUs handle them one after another, sequentially.
So the performance gains were just astronomical.
Yeah, by 2011, using GPUs was making training speeds something like 60 times faster than on CPUs. Researchers finally had the horsepower to tackle problems that had been computationally intractable for decades.
And this convergence led directly to that watershed moment in 2012, which everyone sees as the true start of the third summer.
The ImageNet Large-Scale Visual Recognition Challenge, ILS-VRC.
And AlexNet, a deep convolutional neural network from Geoffrey Hinton's group, just blew the competition away.
By a massive margin. Before AlexNet, the best methods were still classical machine learning, where humans had to manually tell the machine what features to look for in an image. AlexNet showed that if you combine deep learning algorithms, massive GPU power, and the huge ImageNet dataset, the network could just learn the important features all by itself.
And that one event in 2012 basically established deep learning as the dominant paradigm, and that's what kicked off the boom we're in right now.
Since then, it's just been one deep learning success after another. AlphaGo beating the Go world champion in 2016, and of course the recent explosion of generative AI and large language models like GPT-3.
So that brings us to today. With all this investment, all this hype, what seem like daily breakthroughs, the historical pattern makes you have to ask, are we heading for a third AI winter?
We have to be extremely cautious. The core ingredient for a winter is always the same: a massive, unsustainable gap between overhyped expectations and what the technology can actually deliver.
You see that pattern today?
I do, particularly with the ambitious promises around generative AI and all the hype around reaching artificial general intelligence, or AGI.
So if these short-term revolutionary promises, like, say, fully autonomous cars that work everywhere, or an LLM that can truly reason like a human, if those aren't met in the next few years,
that disillusionment could easily lead to major funding pullbacks from VCs and governments. And the technical limitations are still absolutely there.
How so?
Well, even today's incredibly powerful large language models, for all their fluency, they still fundamentally lack true common sense. They're amazing at pattern matching based on their training data, but they don't have a genuine understanding of the physical or social world. They are highly skilled mimics, not thinkers.
And there's also the concern that the main method that's driven all this recent success, just making the models bigger and bigger, might be hitting a point of diminishing returns.
It might be, where the huge investment in computation no longer gives you a proportional gain in performance, but beyond capability, the very nature of these algorithms creates another huge problem: the black box issue.
This opacity, the fact that we can't really see inside and understand why a model made a particular decision.
Exactly. This lack of interpretability is a massive challenge, especially for critical applications. When a deep learning model makes a decision, granting a loan, recommending a cancer treatment, the logic behind it might be completely indiscernible even to the engineers who built it.
And that might be fine for writing a poem or making a funny picture.
But it's a non-starter in fields where accountability is paramount. Doctors, regulators, judges, they need to be able to trace the logic of a decision. If a system makes a mistake or shows bias, you can't fix it if you can't figure out why it made that decision in the first place.
And that lack of interpretability just makes the problem of inherent bias even worse.
Much worse. Because we know these systems train on vast amounts of human-generated data, from Wikipedia to social media, and they inevitably absorb all the systemic biases in that data, gender, racial, political biases. The more complex the model, the harder it is to audit and correct those biases.
Which could lead to a massive loss of public and regulatory trust. And that could trigger a funding collapse, just like technical failures did in the past.
Absolutely. So the strategies for resilience today are all focused on these issues of trust and explanation. The field is actively trying to avoid the next winter by prioritizing transparency and accountability.
So it brings us back to this fundamental tension in modern AI research: the trade-off between performance and interpretability.
It's the central challenge. You can visualize it pretty easily. On one end, you have simple models like linear regression. They're highly interpretable. A human can easily trace the logic.
But they're not very good at complex tasks.
No, they lack the complexity to do things like image recognition. They're reliable, but often not very effective.
And on the other end, you have the deep learning models. Incredibly accurate, but they're the black box, opaque and unexplainable.
And the requirement for real-world deployment in critical areas is that AI systems have to be visible, intelligible, and explainable, not just accurate. A system diagnosing a medical image has to be able to explain which features of the image led to that diagnosis, so a doctor can apply their own judgment.
So if we can't solve this tension between accuracy and explanation, the use of these black box models is going to stall out, which could lead to a freeze. So how does the field solve this?
Well, the path forward seems to be convergence, a reconciliation of the two schools of thought that have been at odds for decades. The symbolic school, which valued logic and explainability, and the connectionist school, which values learning from data.
So we're talking about neurosymbolic AI, NISI AI.
This is the rapidly emerging field that's trying to get the best of both worlds. The goal is to combine the powerful pattern recognition and trainability of neural networks with the explainability and logical consistency of symbolic systems.
So the neural network would do the front-end work, recognizing a cat in a picture, and then feed that into a symbolic system that applies rules and provides a clear, traceable reason for its final conclusion.
Precisely. This hybrid approach could solve so many of our current limitations. It could help with training from smaller data sets, improve error recovery, and most importantly, deliver that critical explainability we need to deploy AI responsibly in high-stakes environments. It's an attempt to prevent the brittleness that doomed the old expert systems while keeping the massive performance gains of deep learning.
You know, when you look back at both of the big AI winters, the final overarching lesson just seems so clear. The price of over-exaggeration is always, always funding cuts and academic stigma.
The current boom is exciting, but the field's long-term success really does rely on humility. We have to manage expectations, prioritize economic viability, be transparent about the limitations, and just focus on incremental, responsible progress, not chasing the sensational, revolutionary hype.
And the stability we have today is really built on those stronger, more rigorous mathematical foundations that were forged during those cold seasons of the past.
Exactly.
And as we think about today's successes, the generative AI that really does seem like magic, it's worth thinking about this recurring historical phenomenon known as the AI effect.
This is such a fascinating concept. The idea that once an AI method becomes common and truly useful and integrated into our daily tech-like handwriting recognition or route optimization or even just spam filters, we stop calling it AI.
Right. The goalposts are constantly moving. AI's success is often measured by its disappearance into the background. It stops being this scary artificial intelligence and just becomes software.
It really makes you wonder how quickly today's miracles, the generative text models or image generation, will just become tomorrow's boring integrated utility. Another piece of software that no one bothers to call AI anymore because it just works.
Maybe the true sign of stable progress is when the hype finally fades and the technology just integrates itself so deeply into the infrastructure of our lives that the concept of a winter becomes obsolete, because the utility is just too integral to ever remove. A truly fascinating perspective.
Absolutely.
Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.